Solar Eclipse 101. Hopefully this video that you get to watch and participate in will help you prepare yourself and the students for a great phenomenon that's coming right in your own backyard. We're all about science phenomena, and this is not only is this for everyone, but for everywhere. Because whether you like it or not, this is coming here. It's going to be something pretty amazing. So I thought we might start by, who are the players in a solar eclipse? This solar eclipse, it says in the name what it is. Solar eclipse, the covering of the sun. If it's a lunar eclipse, it's the covering of Luna, the moon. So that's the first thing we can think about. So the players in this amazing thing are the sun, the earth, and the moon. And I know we taught to our students years ago that to make a shadow, you need three things: a light source, an object, and a surface. In this case, our three players, the sun, the moon, and the earth, will put this beautiful shadow. So the first thing you need to know, I think, is that instead of just calling it shadow, we're going to use a fancy science word, an old word, umbra. Umbra. Maybe you heard the word umbrella, which is to shade something. So we're going to have an umbra, we're going to have a penumbra, and so let's take a look at the first thing that we want to talk about. Is our first player in this is the sun. I know a lot of you are studying the light spectrum, the electromagnetic spectrum, and the part we're going to be concerned with today is just the visible light. But you also have to worry about the UV light and what it can do to our retinas. We'll talk about that in a minute. I don't know if you can see right here, but I have a little bitty spot right there. That is the earth compared to the sun. So once we meet the players, we're also going to have to learn something called scale. And when it comes to scale, we have both size and distance. So there's two parts of that. So just for our purposes today, I made all three of our players the same size. And I know that we teach about design process in our classrooms. So we're going to make a model, and this model has constraints. It's designed to do certain things. In fact, all the models we look at will have limitations. So it's good to know the limitations before we start. This is really good for fitting in front of you, but its limitation is it's not to scale. And I've got our 6 foot in diameter sun, a star. We call it Sol. That's where we get the name solar system. And for many times in the past, we thought that we went around the sun. And it was called, the heliocentric. And at one time we thought that the sun went around us, the geocentric. But getting back to scale, I put some sunspots on here. I put some solar prominences, or some flares that you might see. And I also have the Earth. Here is, to scale in size, what our Earth looks like next to a 6 foot sun. Now, that's one thing that just kind of blows me away, that this can be this comparison. We could put 109 of these across the equator of the sun. The sun is amazing. The sun actually does rotate. Here's a weird thing about the sun. The polar caps takes about 36 hours to rotate, whereas the equator, 25. It's this strange ball of hydrogen crashing together. Someone asked me, is the sun on fire? And the answer is no. If you think about it, you can't have fire unless you have oxygen, heat, and fuel. We have plenty of fuel, but if you take a look at, I have here 2 hydrogen. Here are 2 hydrogen molecules. That's what the sun is made out of. In fact, 99% of the universe is made of hydrogen. And you hear this phrase that we came from dust, we will go back to dust, stardust. It's hydrogen. I like to say the OG, the original gas of the universe. So here are 2 hydrogen atoms, or molecules, that they're crashing together on the sun because of the gravity. When they come together in this model, what you see coming out of there is light and energy. So when 2 hydrogens come together, they make energy that we know that comes from the sun. Come together, make energy. But what also happens in this nuclear fusion, every time these crush together, they give off all that energy, they are destroyed and changed to helium. So it's a really cool thing that's happening every nanosecond on the sun. We get hydrogen crashing together, turning into helium. In fact, helium was first discovered on the sun before it was even discovered here on Earth. So just a little bit about our sun, which is pretty amazing. that it is the anchor of all things. As a matter of fact, you probably don't miss this opportunity to talk about what holds our solar system together. The sun's gravity. Very enthusiastic, thank you. The sun's gravity holds it together. And so I'm sure many of you have done this. In this model, we're switching to another model. I am the sun, Sol, a star, and that purple ball is a planet, let's say the Earth. And this actually happens with the moon and the Earth also. The larger the object, the stronger the gravitational force, the closer it is. And what happens when we don't have gravity? What's going to happen is this won't be going in an orbit around the big gravity. It will be going further off into space, and we'd all end up in a very different world. And this is one that I think that you might like. Once again, our players: the sun, the Earth, and the moon. And I've selected a ping pong ball, and the ping pong ball is 1.5 inch in diameter. And then I've selected, so the moon is about 1/4 that size. So here is a bead, 3/8 inch. Now the interesting part, now we have the correct scale, okay? So the scale is good, but what about the distance scale? And if you do the math on this, this ends up being 9.5 the circumference of the object. So if this is 1.5 inches times 9.5 makes this 42 3/4 inches away. Now that's pretty cool. Here, hold that for me, Brandon. So if you, he's got the moon on a little toothpick there, and the moon is coming around the Earth. Go ahead and stand up. And as you see, we'll do a little switcheroo right here. As that goes around every 29 and some days, too bad it's not exactly 30. Too bad the math is not exact here. It would be a lot easier to predict solar eclipses. Thanks. Now, if you hold that right there for a second, can I get someone else to hold this here? Keep them up. I want to show you something that to me is pretty amazing. If you take a look at this, here is the sun, and if you hold that up just a little bit, and maybe you can see on the wall over there his fingers and such. But the thing I want to show you, look how you have to be exactly lined up in order to get both of those in place. If Brandon, move the moon down a little bit. If Brandon moves the moon down, we don't get a shadow on it. Now move it up. And so, can you imagine as, go ahead and rotate around. Come over this way, guys. Can you imagine as this is rotating around, this sun, there are 2 times a year where they're all lined up. Only 2 times a year. Stop right there. A lot of the times, see how Brandon is below the Earth? This is called the elliptical. It's a fancy word for a plane. And other times in the year, he's above as he goes around. That's about a 5 degree. So we have 2 times in the year. We call it the eclipse season. We just lost the gravity of the Houston, we have a problem. There are 2 times during the year, about halfway over this way, Brandon, about halfway when these guys will line up, and you can have, coming from this side where you can have an eclipse occur on the surface of the Earth. Thank you, guys. So we have the materials for you to make this. This is the Earth-Moon model. We'll send you home with all that today. This might be an easier one, but when we change, this gets even more difficult to show in a classroom. I'll be the first one to say every picture you've ever seen in a book or on the internet that shows the sun and the planets is wrong. It just wouldn't fit. If you tried to get them together, you'd have to use a microscope to see the planets. All right, so I need another volunteer. Thanks. There we go. So here's our Earth, our moon, and it's about that's about 6 inches, so this is about the correct scale to size. And if we go 9.5 times the circumference, let's see how far this goes. So now you just keep backing up and let's see. And this, if you remember, the Apollo missions or the Odyssey that landed on the moon last Sunday, you can see how this gets to be pretty interesting at this scale, the moon going around the Earth. And now, I don't know if you can even see that. It's difficult with this setup. We can see the shadow there. I have to hold this even further back, maybe to see the shadow there. But up here it's too high, out here it's too low. Twice a year, they line up perfectly. So we have one more model that maybe we can gather around and see these over here. You guys want to come a little bit closer and see this? Let's do it right about this table right here. Let's do it over here. So, or should we move Mr. Big Gulp out of the shot?
Yeah.
Okay. You want to grab those other things over there, and you guys want to come close if you want to see this a little bit better. This is another model you can make. Thank you. This one is called it's from the Exploratorium out in California, and it's really hard to show this unless you have animation. If you have animation, it's easier. So here's my Earth cup, okay, and here is my ecliptic. The ecliptic is a line going right through from the sun. If this is going to be the sun, a line going right through here. Now, if I put the moon and I offset it on that little, you see how it's offset there? Let's leave this here. First thing I could show you is, if this is the sun, first thing we show you is, what is it called when we take all this time to go around the sun? What is that called? A revolution, a year. So you could show the kids that. Another thing we could show is this, in place, what is it called when the moon goes around the earth? An orbit, or a month. There's 12 of these months. But the interesting part is this, for me. Because this is tilted, that's the elliptic. If we didn't have this tilt, the moon is tilted down 5 degrees off of the sun and the Earth's ecliptic. If it wasn't, we would have an eclipse once a month, because it would go into that blockage. We'd have an eclipse every month. But it's not, it's tilted. So you won't get an eclipse like this because it's too low. See how the shadow here is too low? 6 months later, when it's up here on this, you're not going to get an eclipse because that shadow is going to be way out in space, too high. But twice a year, when the sun, it's just right about in the middle here, you can see as it rotates around, you can get a shadow, and this is kind of a large shadow right there on the Earth. Can you see the shadow on there? Those are the players. We have the Earth, the Moon, and there are lots of resources out here. Basically, it's a shadow, an umbra that's going to land on the Earth. We have been studying these and documenting them for about 3,000 years. There are Babylonian cuneiform clay tablets where they have marked down these. And there are the Greeks studied them, the Romans studied them. So we have records going back. So the big question is, how do you predict a solar eclipse? And it wasn't until we started bringing math from the Egyptians and some of the other cultures in to actually survey and add the math to these. There's a thing called a cycle, Saros cycle, that every 72 months and maybe 18 days, this whole thing repeats itself. It's pretty complicated. They started like 3,000 years ago to try to calculate that with the math. So twice a year, we're going to have an eclipse somewhere on the Earth, and twice a year we need a new moon, and twice a year it's probably going to be on the ocean. So we're having the one coming up here in Indiana, coming up in about like 35 days, April the 8th at 3:08 in the afternoon. And we're going to be right in what's called the path of totality. So some kids, like another question that I get asked a lot is, how come if the sun is so big, how come the moon, which is so small, can block it out? And so you probably have done this experiment yourself, like if you have take one thumb, put your thumbs out like this, and you notice that they're both the same size. If you shut one eye, if you bring one closer to you, it gets much bigger, right? It actually can block me out. If you do it right now with far out, I'm not blocked out, but if you bring your thumb closer to you, it'll block you out. And one way I did it with this, there's something you can make in your classroom. I have a little shoebox here. And if I open up the shoebox, I have 2 discs, okay? But they're not the same size. Take a look at these discs. See how one's large and one's small? But if you close the lid and get a little bit darker, you can make the big one look really small and the small one look really big, depending upon your apparent position to the two. So that's a good way, or you can do it with a ball, laying a ball down and have kids select. So getting kids to see that is pretty amazing. There's a lot of books out here, a lot of books for kids to learn about and use. One of them, Indiana's Guide to the Total Eclipse, tells about what is the optimum time and place to view the eclipse. The eclipse is going to start in the Pacific Ocean early when the sun comes up. It's going to go across Mexico, and it's going to go through, I think, 13 different states. And we're lucky it's going to come right transect Indiana. So there's going to be viewing spots all along Indiana with more time of totality. So another thing that we want to talk about are the stages of the eclipse. Since things are moving, the actual umbra on the ground is going about 1,000 miles an hour. I don't know if I had the money, but you can buy a ticket on one of the airlines and fly and follow the eclipse in the air above the clouds, and there's going to be a 7-minute and a 12-minute duration. So you could see a solar eclipse for like 20 minutes. And that's pretty amazing because we've made discoveries during a solar eclipse. It's the only time we can see the atmosphere of the sun, the corona. The corona, we didn't even know what it was like until we first saw this and started observing it. It's actually hotter than the sun, which is weird. There's actually, you can see solar flares. And when I showed you about the hydrogen, the sun is not a solid, it's not a liquid, it's not a gas. It's a fourth state of matter called plasma, electrically charged particles that shoot off bigger than the Earth, but because of the sun's gravity, they're often pulled back in. So it's hard to imagine to tell kids that a sunspot is bigger than the Earth. So a lot of cool things, aurora borealis, because of the period of the sunspots. So this is the corona. We will be able to see stars. We'll be able to see stars during the day. And this is the one thing I hope you take advantage of. During the eclipse, take a moment to look around you. In fact, look 360, because we are often used to looking at a sunset going down. When the sunset's going down in the west, that light is coming through our atmosphere and being bent like a rainbow. And I have never seen the green, but all the colors are there. Roy G. Biv, red, orange, yellow, green. So we often see the red and then the orange. Those are the different light spectrums being refracted or bent. On the day of the eclipse, if it's a clear sky, you'll be able to stand. It'll be red there. It'll be red there. It'll be red 360 degrees around you because it's like a sunset going down everywhere. That's going to be pretty amazing. I would suggest you with your family and students also make a journal, write something down. Who are you with that day? What did you notice that day? How much, did anything weird happen? Did the temperature change? Did you see animals do something? Were birds going to bed? You know, write down, because it's going to be one of these things, and I tell everybody, hey, if you miss this one, we'll have another one somewhere in North America in 2044. But the next one that's going to come to Indiana is going to be 221 years from now. So don't miss this one. It's going to be worth seeing and doing. So lots of different activities to try. One we need to talk about are glasses. Let me show you the glasses. So these, you can buy these or get fancy ones. Our school district has made an investment in education and the safe viewing of the solar eclipse. If you're going to use direct viewing, which we encourage you to do, these glasses, make sure you inspect them, that they're not scratched or dented or broken, because these are not sunglasses. There's no pair of sunglasses you have that are strong enough to protect your eyes. In the back of your eye, in the front of your eye, you have a lens, and this convex lens intensifies and focuses light. So it's basically, when you look at the sun, you're putting a magnifying lens to intensify that energy to the back of your retina. And within a minute and a half, it will burn, even less, depending on the circumstances. It will burn a hole in the back of your retina. Why do I know this? Because I had a hole burnt in the back of my retina. It's not a good thing. Not from the sun, though. So you don't want to view the sun directly. And so some kids are going to say, well, Mr. Crosslin and I, we watched the sunset go down. When you see a sunset, you're maximizing the amount of atmosphere you're looking through. And so you're offered a little more protection. But even staring at a sunset is not that good for you. So you want to wear your special, we're going to call these Eclipse glasses. You want to put them over your regular glasses. They don't really work with binoculars or anything else. Don't put them in front of binoculars and try it, because that would just intensify the lenses and burn a hole right through these, and then your retina. So this is, when do you use these? Well, there's 5 contact points during the eclipse. When it first starts coming, when we don't see it, you're looking at the sun, wear these. You'll be able to see sunspots, maybe something else you might get to see, so put your glasses on. At first contact, that's when the moon, the moon actually starts to be in the disk of the sun. It's called first contact. Wear your glasses. It's going to be like a Cookie Monster eating a big cookie. You'll see a piece of it. That's first contact. That's going to last from when it starts about an hour, maybe 90 minutes, until something we're expecting to see, which is the second contact. Right when the disc is almost completely covered, you're going to get what's called the diamond ring. It's going to be like a brilliant diamond at the side of it. Wear your glasses. It's still. And then when that completely covers it, that ring goes away and you see the corona, which is totality. That's when you can take these off. Now, depending on where you're at, we're going to have like 2 minutes and 30 seconds of viewing this. Here's some tips. Because I did some research on what happens to your eyes, one, they suggest have someone with a red shirt and a green shirt on, because the way our cones and rods work in dim light, some colors get intensified and some colors are subdued. Red and green are the two that will have a kind of cool effect. The other thing to do is try to, after 8 seconds of watching without the glasses, 8 seconds, look away, give your eyes a rest, and look back up. I've been told that by doing that, it's a better opportunity for your eyes to adjust and see all these things. Now, these are a must. After that 2 minutes and 30 seconds, resist the urge to see the diamond ring again, or Bailey's beads. There's a thing called Bailey's beads. Because the moon is not completely flat, there are craters on the moon, and what you'll see is the sunlight piercing through these craters that look like little beads, beautiful, brilliant beads. And resist the urge to look at them with your naked eye, because those beads are like darts going in the back of your eye. You'll put your goggles on quick. So get your glasses back on. But I'm suggesting we do one more thing. I made these with the kids. Maybe you can make these. This is the original, the one and only Total Solar Eclipse Corona Mask. And so I got my glasses on the back here. This might be the best thing ever came out. So the eclipse is coming. It's been documented over the ages of time, from the Greeks to the British. Everybody has stories about eclipses. It wasn't until science came on the scene with measurements and observations and recording that we understood better the cycles of these things. And once again, in this model, we have constraints, but as you can see here, if I'm going to be the Earth, here's the moon rotating around, turn the light on, and if we get this just right, maybe you can see a shadow coming across my face. Yes? So, and unfortunately, if we get off 5 degrees, you can see that no shadow until I get to that one time during the year when I have everything lined up just right. And that would be the eclipse season. So these are some tools to get kids excited, to be better prepared for this phenomena that's going to happen April the 8th at 3:08. Whoever you're going to be with, you want to document that. It's going to be a once in a lifetime. And I can't wait for you guys to experience it. If you don't want to use the glasses, I brought all this material for us to make. This is a solar eclipse projector, a pinhole projector, and it took about less than 2 minutes to make. What I have here is a piece of aluminum foil with a pinhole put in it and a viewing port here. And on the inside, I put a white piece of 3x5 index card. And so if the sun is here, Brandon, be the sun again for me. And go ahead and light my back of my head up, and so and the sun goes in here, and I look into this, and I can see the eclipse right through here. So that's a very safe way to do it. Back to the sun. You can do as simply as easy as putting your fingers like this. Shine the light for me again from the above onto the ground. Here's our three things. We have a light source, an object, and a surface. And see those lines you see on the ground there? You would see 6 or 7 solar eclipses. If you bring a strainer out, I even took a straw hat with all the little lights going through, I saw about 100 eclipses on the ground. And they will change as the eclipse change. And probably one last thing, if you find a place that has a tree, you heard the word dappled sunlight, a dapple where the light comes through. Animals make use of it for camouflage. A deer has little spots. Go under that tree during the solar eclipse, and on the ground, moving with the wind, will be thousands of eclipses. So as long as I hope you have an enjoyable time. I think an informed mind makes these opportunities even better for us. So learn a little bit about it, teach it, make some things, have fun.